Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leader series, Sustainable Asphalt Reinforcement and Material Selection. My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past and present. Before we get started, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Huska Australia Proprietary Limited. Now today, we will hear from two speakers followed by our live audience Q&A, so I encourage you all to please send your questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Professor Jorge Zornberg, Professor and Joe J. King Chair in Engineering at the University of Texas in Austin. Professor Zornberg has over 35 years of experience in practice and research in geotechnical and geosynthetics engineering. His research focuses on transportation geotechnics, geosynthetics, unsaturated soils, expansive clays, and environmental geotechnics. He served as president of the International Geosynthetic Society, IGS. He has authored over 550 technical publications, written several book chapters, and been awarded 3 patents. Professor Zornberg received numerous prestigious awards, including the Presidential Early Career Award for Scientists and Engineers from the President of the United States. The IGS established the Zornberg Lecture and Honorary Lecture, recognizing his contributions to the discipline of geosynthetics. So please join me in welcoming Professor Jorge Zornberg.
Thank you very much for the introduction. It's such a pleasure to be making this presentation for Engineers Australia. I'm going to be talking about geosynthetics or sustainable asphalt reinforcement. Geosynthetics have been used for asphalt and in roadways in general. Probably this is one of the earliest applications of geosynthetics in roadways, maybe dating back to the 60s. But as in much of what we do in roadway design and in geotechnical design in general, our discipline is quite of a reactive discipline. So even though we do know that this works, this technology works, it is only now that we're making significant advances to understand why is that they work as they do. So the objective of this presentation is to walk you through some recent advances, particularly on the mechanisms, properties, and some new benefits of geosynthetics for asphalt reinforcement. Okay, so the initial reason why we use geosynthetics in asphalt is to mitigate or delay the problem associated with reflective cracking. What is this? As a strategy for improving the performance of roadways, a very common strategy is that once we have a cracked pavement, we typically may end up doing a conventional rehabilitation, which means essentially perhaps milling a superficial portion of this cracked pavement and then constructing a thin asphalt overlay. There's a problem, however, and that problem is that because of the solicitations to which the new asphalt is subjected to when in contact with pre-existing cracks, the phenomenon known as reflective cracking may very well happen and in comparatively a short period of time. So the main objective of using and the primary use of geosynthetics in as a reinforcement for asphalt interlayers has been to mitigate, delay this reflective cracking. So let me walk you from the very beginning. So we're going to be talking about mitigation of asphalt reflective cracking. And the objective is, as I have mentioned, retard or ideally eliminate the reflective cracking into structural asphalt overlays. Now, why do we have this problem associated with reflective cracking? Well, it turns out that if our wheel load goes on top of a brand new overlay, but the new overlay is sitting on top of a pre-existing crack, it turns out that there are very significant localized mechanisms that essentially will trigger the crack in the new overlay. This happens, if you think about it, the wheel is advancing, approaching the crack, and it's causing shear. And as soon as it's over the crack, it causes bending. And as soon as it's past the crack, it causes shear in the reverse direction. That is a significant solicitation to our brand new overlay. And in some cases, for example, when we have an asphaltic layer on top of a concrete pavement, we may also have problems associated with pre-existing cracks or joints in order to mitigate thermal movements. Okay, so the idea is that in order to mitigate these problems or delay these problems, essentially what we have is a stress concentration, and the cracks are generated because of a concentration of energy that will trigger the crack. And in order to mitigate this problem is that we have been using geosynthetics, that is polymeric materials that we use in combination with soil or asphalt in order to advance or resolve problems in geotechnical engineering and in transportation engineering. Now, let me tell you about the mechanisms of why these geosynthetic will work when used to reinforce asphalt layers. And I'm going to give you 3 different reasons, and they all work, but they are not necessarily they not necessarily add one to each other. And I'm going to come back to illustrating or explaining a little bit more what each one of these mechanisms are. The first mechanism that I'm going to discuss is what we call tension development. So essentially, what the geosynthetic will do is a stress redistribution, so that rather than having a highly concentrated stress in a very localized, local point, we're going to redistribute those stresses so that we are not going to trigger the crack. There is a second strategy that is typically identified as stress relief. In this particular case, we're going to educate the crack on how to distribute, on how to grow, and we're going to educate it so that it doesn't get into the brand new asphalt overlay. There is a third mechanism that complements the previous ones, and that is a moisture barrier. And the concept is that if we happen to generate this crack happens to reflect. At the very least, we want to protect the structural component of our pavement so that water does not migrate past the interface of the new asphalt overlay and the pre-existing asphaltic layer. Let me get back to each one of these, particularly the 2 initial ones, to clarify what I mean by these different mechanisms. Here's the first mechanism. So essentially, we do have, you can see in the figure, a zoom out of a pre-existing crack. And on top of this, we have our brand new asphalt overlay. If we do have, in this section, we do not have a geosynthetic, what will happen, and as I mentioned before, because of shear, because it's bending, because of shear reversal, we're going to have the reflection of this crack. Instead, if we do have the geosynthetic reinforcement, but now and good bonding, what is going to happen is that when these shear solicitations occur, we are going to distribute those tensions over a comparatively wider area in such a way that we do not have the concentration of stresses that will trigger the crack. This stress redistribution is essentially what leads to the retardation, or ideally to the complete mitigation of this reflective cracking mechanism. That's one of the strategies, one of the mechanisms. There is a second mechanism, and that is the mechanism of stress relief. In this case, what is going to happen is that rather than having a geosynthetic that develops tension, what we are going to do, again, if we do not have a geosynthetic here, will happen the same as what we had before. We are going to have localized displacement, localized stresses, and the crack may end up being triggered. Instead, if we put a geosynthetic that will act as a stress relief, with stress relief mechanism, what we're going to do is we're going to educate this interface so that the displacements that occur in the vicinity of the pre-existing crack are not transferred to the new overlay. Or if they are transferred, that we minimize the transfer of those displacements, of those stresses from the vicinity of the pre-existing crack into the new asphalt overlay. Essentially, what we are doing is we are educating that in a controlled manner, we transfer this energy that will develop the crack, but along the interface between the pre-existing asphaltic layer and the new asphalt overlay. So here we have it, two very different, significantly different mechanisms. They will require both of them mechanical, but they will require different properties. It is only now that once we have I have identified the mechanisms, is that we can go to the next step in the design using geosynthetics, which is identifying the functions. And what are the functions that we're going to have? What are the functions that the geosynthetic is going to be doing? Well, it depends on the mechanism that we're talking about. If we're talking about the stress redistribution mechanism, we are talking about a reinforcement function. In the design of geosynthetics, when we have put our finger in the function, essentially we're very close to defining what are the properties that matter. So here is one of the mechanisms, essentially makes our geosynthetic work as a reinforcement. This is different than the second mechanism, that is stress relief. In some agencies or some guidelines identify stress relief as a function in itself. I'm going to put it within the family of separation as a function, and essentially the properties that we will require in order to develop this second mechanism are going to be very different than the properties that we have in order to develop the reinforcement. So this is one important lesson learned. We can ask the geosynthetic to work as a reinforcement for stress redistribution or as a stress relief layer in order to, both of them will retard or eliminate the reflective cracking. What we really cannot do is to ask a geosynthetic that work in both mechanisms. They require different properties. Now, it turns out that the barrier function that I have also been discussing can work in isolation. We can have a geosynthetic that only works as a barrier and not necessarily to mitigate the reflective cracking, or this is one of those functions that we can combine either with reinforcement or with stress relief. All right, so now that we have identified what are the mechanisms that make the geosynthetic work, and we have identified the functions of the geosynthetic to work in order to mitigate the problems associated with reflective cracking, is that we can get into the geosynthetic properties. For example, for the case in which we have the tension development mechanism, which is the first of the two mechanical mechanisms that I have discussed, the properties that we're going to that have typically been identified are going to be tensile strength, which is characteristic of a geosynthetic as a reinforcement layer. We're also going to have the unconfined tensile stiffness. We're also going to have the asphalt retention. I'm not going to get into the details on how to get these different properties, but this has to do a lot with how the bonding is going to occur between the geosynthetic and the asphaltic layers. We may have survivability-related properties. Essentially, the geosynthetic should survive the installation and the long-term performance. And we may have to characterize the interface shear characteristics. And I'm going to also give you a brief and this presentation is on advances in the use of geosynthetics for asphalt reinforcement. So I'm going to show you a new property that I believe that is particularly relevant when using geosynthetics to mitigate reflective cracking. Okay, here we have gone from the mechanisms to identify the functions to define the properties. And ultimately, what are the benefits? Well, the benefits are essentially we're going to maintain the integrity of the structural asphalt overlay by retarding or ideally by eliminating these reflective cracks. And by mitigating or eliminating this reflective cracking, we are avoiding the mechanisms that of degradation of our entire structural package that typically will get initiated once we have water intrusion. Very good. So it turns out that there are many different types of geosynthetics that can be adopted. I'm going to call them here as paving geosynthetics. And this may be good in the sense that we do have many different options, but it may not be that good because essentially we need to understand the different options. And as I mentioned, at the very least, we have at least 3 different mechanisms that we can tap into. Not all geosynthetics are going to work in each one of them, and we need to understand what are the properties that are going to make them work. The geosynthetics that have been used as paving geosynthetics include geotextile fabrics, include geogrids, in this case glass geogrids made out of polymeric materials or of glass materials. Here it is, glass or polymeric geogrids. In addition to that, we have geocomposites. In some cases, we're going to have typically geogrids that are going to do the mechanical work, and we're going to incorporate a geotextile in order to facilitate the installation. Because one aspect that is particularly important is that the installation of these paving geosynthetics needs to be particularly good, no wrinkles, for example, and the presence of geotextiles, particularly if they are particularly thin, they are going to facilitate this installation without compromising the performance of the geogrid. And we're going to have, and I'm showing here products that are common in the US, but I assume that these are also common in Australia. Hybrid geomats, typically a combination of polymeric materials with fibers. And in some cases, for example, when we have a concrete pavements, rigid pavements, and on top of which we're going to put an asphalt overlay. Sometimes we are going to protect with interlayers that do not cover the entire surface, but only on top of what we know that is going to become a interlayer, a reflective crack, or we have the potential to generate a reflective crack. I'm going to go very, very quickly through the installation, just for you to have a sense of what this involves. Installation is going to typically start with the milling of the pre-existing asphaltic layer. In some cases, we're going to have some sealing of on the surface, some work that can be done on the surface. Then we typically are going to have in the US, we typically are going to apply a sealant tack coat, in this case AC15P. There are different types. In some countries, not in the US, we use emulsions. And after applying the sealant tack coat is that we're going to come with the installation of the paving geosynthetic. Among the different uses of geosynthetics in roadway applications, I could say that the use of geosynthetics as for asphalt reinforcement is probably the one that requires the most care and the most experience. It's not difficult, but we need experience in order to properly install the geosynthetic for this particular application. And here we see the installation of a geosynthetic, in this particular case, a polymeric geogrid. The equipment is, I would call it conventional equipment, but it requires some adaptations. For example, in this case, to make sure that we do not have wrinkles in the unrolling. Essentially, what we're doing is we're unrolling a roll, but we need to do it in a proper manner in order not to have wrinkles. Here we have the same exercise, but in this case with a glass geogrid, with a glass grid. In this third example, and I'm showing you examples of a particular project, and I'm going to come back to this project because it's a project in which multiple types of geosynthetics were used as paving geosynthetics. And in this particular case, here we have the installation of a fiberglass mat, a third type of geosynthetic. In this particular case, it's not a geogrid, but a mat. And the good news is that everything that you as a pavement, as a transportation engineer, as a roadway engineer have learned regarding or have used regarding the installation of asphalt overlays, the equipment will be the same, the care is going to be the same, and here we have the conveyor for the construction of the new asphalt overlay in a conventional manner. All right, so we have gone through the mechanisms, we have touched on the properties, we have gone very briefly as an overview on the characteristics of the installation. Let me tell you a little bit about some news about properties. So I'm gonna get now into a recent study that has been done at the University of Texas at Austin, and in this particular case is the characterization of the interface shear strength that will eventually occur between the geosynthetic and the adjacent asphaltic layer. We should not expect the same level of interface shear strength that we have between the asphalt and asphalt if we have a plane that is characterized by a geosynthetic. What is this property has been investigated for quite a number of times, but what is unique about the study that I'm going to show you is that the study was done essentially all of them at the same location, all of them, the construction of all the different types of geosynthetics was done at the same time. Essentially, we're talking about all of them subjected to the same weather conditions, to the same traffic conditions. So it's a field study, while most of these are not samples, geosynthetic sample, asphalt samples that have been created in a laboratory setting. These are cores that have been obtained from an actual in-service roadway. So in the particular case that I'm going to be tell you about, we're going to have an old HMA. Typically, we're going to have a level up, essentially for grading purposes. Then we're going to have the geosynthetic. I'm going to show you the results with 6 different types of geosynthetics. Then 2 types of asphalt mixes. One is going to be a coarse type D, dense asphalt mix, and then TOM. TOM stands for thin overlay mix. And okay, so here is one of the various cores that are going to be tested. This testing was done using the Leutner interface shear strength testing setup. Here is a view of one of the samples ready for testing. Here we have the load frame that was used for testing. As you know, these test results are highly sensitive to the temperature at which these tests are conducted. All the tests were conducted at the same load rate and a control temperature of 22 degrees centigrade. All right, so let me show you the results. So first, I'm going to show you the interface shear strength versus displacement for the control section. That is the section that in which we have the pre-existing asphaltic layer with the new asphalt layer, not geosynthetic. And here's a shear versus displacement curve. Then we're going to have one with a geosynthetic reinforcement 1. And as expected, the interface shear strength is going to be lower. And what is important to note is that not necessarily all the geosynthetics are going to perform the same. It is expected that the interface shear strength will be lower than the control without geosynthetic, but the magnitude is something that we are looking into. And here is a geosynthetic reinforcement type 2, and this is a geosynthetic reinforcement type 3. All these 3 geosynthetics in this particular study are polymeric products. And then here we have, again, additional results, the control curve again, but now compared against fiberglass products. Here is a GeoGrid composite with fiberglass number 4, product number 4, and product number 5, and product number 6. In summary, these are important because even though we have gone through this characterization in a number of studies, previous studies, this is, I consider that is particularly relevant because this is from, all of them come from cores, from a roadway in which the asphalt overlay was constructed in all of them at the same time. So they test the aging and the characteristics of the asphalt mixes and the characteristics of they were all done with by the same installer. So this is I consider that is a particularly valuable and consistent field approach. So ultimately here are the different results. In black, we have the interface shear strength or peak interface shear strength for the control section, asphalt against asphalt, not geosynthetic. And here is the magnitude of the interface shear strength for geosynthetic 1, 2, 3, all 3 polymeric geosynthetics, 4, 5, 6, all 3 glass grid geosynthetics. And here is the displacement at peak. Typically, but not always, the displacement at peak is slightly higher, has been, at least in this testing program, has been slightly higher than the displacement at peak. Again, black is the control section. All right, so this was interface shear along the interface between the geosynthetic and the adjacent asphaltic layer. But if you think about it, when we're talking about reflective cracking, it's a different type of shear, the one that matters the most. How come? Because really what we're doing, if this is the geosynthetic, what the shear that we're talking is a cross shear. So a second study that I'm going to show you now involves the analysis and the evaluation of reinforced specimens, in this case, laboratory specimens, but shear in a cross direction. The objective is to quantify the resistance and compare against control sections without geosynthetic when we induce this cross shear in a reinforced specimen, reinforced asphaltic layer reinforced with a geosynthetic. This is the type of shear to which realistically the section is going to be subjected to due to wheel loading on top of a pre-existing crack. Okay, so this is one of the samples that were tested in the lab. These are painted white in order to better observe the development of the cracks. This is a schematic view. See, essentially, the specimen is held in place in one half and is loaded monotonically or cyclically on the other half. This is a view of the setup. And I'm going to show you some results of, again, shear, but in the cross-plane direction. First, I'm going to show you some monotonic results. Even though the loading in the field is not monotonic, I think that we can learn a lot from the monotonic loading. This is the shear stress, cross shear in the cross direction versus relative shear displacement of the control section. We're going to have a peak that is on the order of 5%, and then the shear stress is going to drop to 0. Again, we're talking about an unreinforced specimen. Now, when we do the same test, but now with a and one important thing that I would like to highlight is the ductility or the energy. So we are going to have the area under this curve is a measure of the energy that the system will have in order to resist the propagation of this crack. And here we have in blue the pre-cracking energy, and here post-peak, because post-peak the specimen can still take some shear, the total fracture energy, the complete area under the curve. And a different way of looking at this is how this energy increases with increasing relative displacement as the specimen is being sheared. And here we have it, and here we give the name of fracture energy to the total energy that ends up happening at a comparatively large relative displacement. I want to show you as well how this crack visually develops in monotonic testing in this control. That means unreinforced specimen is painted white in order to better identify the development of the crack. Essentially, we notice the crack develops when we reach the peak shear resistance in our specimen, and here's with the shear displacement on the order. This is on the order of 5%, and this is when we have reached on the order of 15%. Notice the shape of this. It's really a fracture that goes all across the entire pavement layer, and there's a full detachment of the two sides of the asphalt sample at each side of the crack that has developed. But now let's do the same test now with a geosynthetic reinforced asphaltic layer. And what you're going to see is that, again, I'm showing you the same curve that I showed you before as a reference. And I'm going to show you now what we obtain with a reinforced, in this particular case, a polymeric reinforced specimen. And we can see some very interesting features. The first feature that we can observe is that the peak shear resistance is higher, and that's good. But I would contend that that's not the only good aspect of having this sample being reinforced with a geosynthetic versus a control without a geosynthetic. Notice the post-peak behavior. Notice the post-peak behavior, and you will see that even though we have reached a maximum shear, the crack has developed. There is continued resistance that happens along that fracture that has developed. And what this essentially will do is that even though the crack has developed, it will remain reasonably closed, and more importantly, this will mitigate or minimize the development of the crack in the longitudinal direction. Why? Because notice the area under the curve is significantly larger than in the control section. It's not only a higher peak, which is good, but also a significantly additional energy, fracture energy, that we are going to have in our specimens when reinforced, in this particular case, with polymeric geocretes. Here are two different types of polymeric specimens, both of them with a higher peak, and both of them with a significantly higher post-peak, we can call it residual interface shear strength. This is the same data coming from the same tests, but in this case, here in black is in the vertical axis, we have the cross shear energy, which is the area under the curve. And once we reach essentially zero additional contribution, the energy that this system could provide it cannot increase anymore. On the other hand, in both cases, in the two polymeric reinforced specimens, we're going to have an an increased, and actually even after reaching, in this particular case, 30% relative shear displacement, the energy that could continue to develop, it would continue to provide resistance to the development of these cracks. I consider that this is a particularly relevant feature of the use of geosynthetic reinforcements to mitigate reflective cracking. I showed you the view of the specimens for the case of the control section, the control specimens without reinforcements. And now, if you remember, the previous one was a very clean and rapid and wide crack that had developed. Is much more measured and much more controlled, a crack that will eventually develop when we do have the at a higher peak interface shears, at the peak cross shear resistance when we have the reinforcement. But you can ask me, well, but this was monotonic loading. In the field, we're really going to have a cyclic loading. That is correct. So we can learn a lot from the monotonic tests, but now let me take you to the cyclic tests. In this particular case, I'm going to show you cross-shear tests, but in this case, the tests were done to a given displacement amplitude, and what we do is we measure the shear resistance as this. I think that the frequency was on the order of 1 hertz, and we can have the shear resistance that develops as the subsequent loadings are applied. 1,000 cycles, 2,000 cycles, 5,000 cycles. These are two curves that are two repeats of the same test on a control specimen, no geosynthetic reinforcement in this particular case. As we can expect, this shear, let's call it shear resistance under cyclic loading, will drop as we increase the number of cycles, and will reach some form of a plateau. We'll reach some form of a plateau. So now, but this type of loading will also depend on the magnitude of the displacement to which we subject the specimen. And in this case, this curve done. These curves were developed for a comparatively small displacement amplitude, but we have a similar response, I would say more rapid response, and we reach more rapidly this plateau resistance. One in this case with a comparatively larger amplitude in this cyclic loading. Again, we impose a given displacement and we measure the shear resistance. Again, in two tests with comparatively small displacements, two tests in comparatively large displacements, I was honestly particularly impressed with the good repeatability of these results. All right, but this was a control specimen, no geosynthetics. How is the response that we should expect from a reinforced specimen? Well, here it is. So here we have as a reference, this is for small displacements. Here is as a reference the cyclic shear versus number of cycles response of our specimens. And here we have with two different polymeric reinforcements, the response. The good news is that, yes, we're going to have this initial drop as we increase the number of cycles, but it's very, very important to notice that this residual resistance is double, or perhaps more than double, the shear resistance that occurs under also cyclic conditions, but in the control specimen, and the same, but potentially even tripled, in this case, the type of response that we do have when we load cyclically, but in this case with a comparatively larger displacement amplitude. So in summary, I have gone through the use of geosynthetic reinforcements for the mitigation of reflective cracking. I walked you through what are the mechanisms. Once we have the mechanism, we have the functions, we have the properties, and then I walked you through some, I would say, more, I'm going to call it newer properties that explain the performance of this, the use of geosynthetic reinforcements to mitigate reflective cracking. But I have some good news. And the good news is that, and we have been using for a long time geosynthetic reinforcements to mitigate reflective cracking, but we always suspected, and there are some field evidences, that in addition, not all, but some of these geosynthetic reinforcements, in addition to mitigate reflective cracking, because if they work as reinforcement, they're expected to provide additional increased structural capacity. But in order to incorporate this into our design, we need field data. And that's what I'm going to show you now. So in addition to the use of geosynthetic reinforcement in asphalt layers to mitigate reflective cracking, I'm going to walk you now through an additional benefit. In this particular case, the use of geosynthetic reinforcement to increase the structural capacity. of the system. I'm going to start by showing you some experimental results. By experimental results, I mean an accelerated pavement testing. This test was done in Brazil. And essentially what I'm going to show you through some initial results on this initial evidence that, yes, we should potentially expect that there's going to be an increased structural capacity. In this case, two models, model 1 unreinforced, model 2 reinforced. The two models will load. The two models are identical, with the only difference being one has a reinforcement, the other does not. Let me show you some examples of the response, only to illustrate this. Here is example number 1. Model number 1, control section. Model number 2, one of the reinforced sections. And as you can see, the profile for, in this particular case, for 10 power 5, 100,000 cycles. Here we have the rutting profile in model 1 unreinforced, and the rutting profile, the permanent rutting, the permanent displacements, and this is clear evidence of the beneficial impact of the geosynthetic in the structural capacity of the pavement. But let me show you another important benefit. In this particular case, I'm going to take you in the vertical axis, total strains, microstrains. Let's have a look at the microstrains, at the elastic strains that develop with each one of the loads. So the top graph is permanent displacements. Now I'm going to take you to elastic strains. And what we see here in black is a response here. Notice here is 99,996 seconds. And here we have one load and the second load and the third load, and with each wheel load, we're going to have a peak in the strains. And here it is, the magnitude of the strain. First, the accumulated strains by this time is significantly higher in the black response, which is the control model, and than in the red response. And also the magnitude of the strains, elastic strains, most of it recoverable, some of it is not recovered, that occur in the unreinforced model is going to be perhaps double or triple the magnitude of the elastic strains that are occurring in the reinforced, in this case, red model. And as you know, the magnitude of the elastic strains eventually is going to reflect itself in the performance of our roadways in the form of fatigue. So smaller elastic strains for a given load will translate in an extended design life, in this case, failure due to fatigue. All right, so this is great news, but this is a model in the lab. What about if we do this, but in the field? And that's what we did working with in an association with the Texas Department of Transportation. I'm going to take you to an important and large project that involved essentially the reconstruction of a comparatively large section across along SH21, State Highway 21, across an entire county. In this particular case, Lee County. And essentially what we're going to do in a fraction of this section of about a mile, 1.5 kilometers or so, we're going to have experimental sections. So this was a real project, an actual comparatively large volume a road that was subjected, it was retrofitted with polymeric geogrids as asphalt reinforcement. But in this case, the Department of Transportation was wise enough to take this as an opportunity to evaluate not the one that ended up getting the bid for this project, but also a number of different types of reinforcements. So I'm going to take you now to what is indicated here as the experimental test sections in this particular project, and this is what it is. Shy of 1 mile, on the order of 1.4 kilometers. And here you have, and thank you, Texas Department of Transportation, because we know that when we have control sections, essentially the department needs to be ready to potentially have a higher additional costs for maintenance of this road, particularly on the control sections. But these costs are going to come back as a significant benefit from the lessons learned in this particular test. And notice that here we're going to have green, red, blue, green again. These are all different types. This is a 4-lane road. And on one of the lanes, in the 2 of the lanes, we're going to have reinforced sections. In the second lane we're going to have a control section. So we will have a direct comparison of white non-geogrid section, in this case, geogrid 1, which is the red, in this case, red section, reinforced and unreinforced side to side. And we're going to be able to evaluate the response. Oh, but one is the inner lane, the other is the outer lane. Yes, that's why in the other lane, we have the control section being the inner lane and the reinforced section being the outer lane. And all these sections in here that I'm pointing here, these first 1,575 feet are instrumented sections. In addition to that, we have non-instrumented sections. Overall, these are the instrumented sections, and the program has included a total of 44 test sections, more than 40 test sections with a combination of 9 different types of geosynthetics, plus control sections, and seven of these 44 test sections were heavily instrumented. Why instrumented? Well, we're going to eventually know the difference in performance of the different test sections on the order of 200 feet each, so on the order of 80 meters or so, each one of these test sections. But we want to know the performance before bringing these sections to failure, which may happen in 5 years, may happen in 10 years, may happen in 15 years. We want to start learning from these test sections right after construction. And that's why we're going to have a heavily instrumented test sections. I'm just going to walk you very briefly through some of the results. So here we have 4 of the 9 different types of geosynthetics: polymeric geogrease, glass grease, fiberglass composites, fiber mat, glass fiber mat. And essentially, I'm going to walk you now through the layout of the instrumentation. Here in plan view, we're going to see what is called asphalt strain gauges, a very, very highly successful type of sensor. We're going to measure the strains that occur upon loading in the longitudinal direction along the wheel path, in the longitudinal direction in between wheel paths, in the transverse direction, both along the wheel path and in between wheel paths. And in addition to that, this is a cross-section, this is plan view, this is a cross-section, here heavily instrumented in the asphaltic layers with thermocouples, asphalt strain gauges, geophones to measure displacements, and moisture sensors. These are some views of some of these instruments: asphalt strain gauges, geophones, multi-directional and one-directional geophones, and moisture sensors. This section happens to be this roadway happens to be constructed on clay, actual expansive clay. All right, so let me show you, there's a lot that I could show you about the construction of these instrumented test sections, but here I'm showing you one of here in the form of a T is the asphalt strain gauges. Here is in the transverse direction. Here's another asphalt strain gauge in the longitudinal direction. Here you have the direction of the traffic. So here we're going to get the transverse and the longitudinal strains with the passage of loads. And what type of, this is during construction, during installation, but then significant number of campaigns to come back to these sites to do, to evaluate the performance as time passes by at different temperatures. This is Texas, high temperatures in many cases, comparatively low temperatures during the winter. And here is some examples of the type of tests that were systematically done over the years: plate load tests, FWD tests. Typically, these tests are done directly on top of the sensors. So we are interpreting these FWD test results not only the classic way, which is with the surface deflections, but we also have the internal deflections. So these are highly reliable. The interpretation of this FWD is highly reliable. And perhaps, here's again the FWD, and perhaps the one that I'm going to focus the most is what we call loading campaigns. Essentially, we're going to have at least two different types of trucks, and we're going to educate the driver. We're going to ask the driver to drive through this blue tape. Why on the blue tape? Because essentially this will be a truck, and we measure the load in each one of the wheels, the axis and axles, and we're going to know the application of this known load, and we're going to go directly on top of the sensors. So this is not, we are also obtaining the performance of the roadway with general traffic, but in this particular case will be of a known load, a load of a known magnitude directly on top of our sensors. So let me just show you one of the examples. In this particular case, I'm going to show you the response of a transverse strains with asphalt strain gauges. And here is a 3-axles truck, and here we have the front wheel and the 2 axles in the rear wheels. Red is the front wheel, and here is the front wheel approaching the location of a transverse strain gauge, asphalt strain gauge, and we're going to measure the response, the transverse strain that occurs on the wheel path as the wheel is approaching the asphalt strain gauge, here is the response. No surprise, it's going to be 3 peaks. So here comes the wheel is approaching. Now we're going to start feeling, the asphalt strain gauge starts feeling and develop these transverse strains. Here's the first peak, and then we are approaches the rear axles, and here is here's the approximation. Here is the first peak. Here we're going to be ready for the second loading, the second peak in this exercise, and here comes the third axle, and here we're going to have how this asphalt strain gauge responses to this known load. In the vertical axis, we have micro strains. In the horizontal axis, time. We did this under control speed, typically 25 miles per hour or 5 miles per hour. Now, what I didn't tell you is that this response, 3 peaks, as we should expect, tensile strains in the transverse direction, is for the unreinforced control section. What about the reinforced sections? So let me show you what we will get. First, again, I'm going to show you the same results, the control section, the 3 peaks that we get with one of the passages on top of the transverse asphalt strain gauge, but in the control section, no reinforcement. And this is the response that we get, same load, same temperature, same weather conditions, same age or same time since construction. The only difference between these two responses is one is a control section, the other is a reinforced section with one of the 9 different geosynthetic reinforcements that were used in this study. If you notice, this is quite similar to the result or the type of response that we got with accelerated pavement testing, but this is a real road, a fully actually a high volume road. And in this case, we know that for a given load, a higher transverse strain will eventually translate into fatigue failure. And in this green reinforced response, we're going to have a comparatively better performance because of a lower elastic strains and consequently less loading associated with the fatigue failure for this roadway. Okay, so I walked you through this new benefit of asphalt reinforcement, which is increased structural capacity. And this is above and beyond the benefit that we already were having of retarding reflective cracking. But let me give you another benefit. I'm going to take you back, but now to this entire, I walked you through what happened in the test sections. I'm going to come back now to the SH21 project, but in this particular case, because I'm going to show you another benefit. I talked to you about the reflective cracking. I talked to you about the increased structural capacity. I'm going to tell you about the third benefit that is becoming more and more important, which is, do we have benefits from the sustainability point of view? So in this particular project, I'm going to walk you through the design of these asphalt overlay that had been proposed without reinforcement. I'm going to show you the design with reinforcement. This is a site that required, it was in need of an overlay, but it was also in need of an increased structural capacity. Why this particular road is within the energy sector in Central Texas, and so the challenges in this particular project was mitigating reflective cracking, but at the same time, it was necessary to increase the structural capacity due to the additional demand that this road was having. Okay, so let me show you these were the design requirements: mitigate reflective cracking, increase structural capacity. So there were 2 competing designs for this project. One was, I would call it a conventional design without geosynthetic. Essentially, it included an asphalt overlay on the order of 12 centimeters thick. But instead, the competing design, which ends up being the one that was adopted, is the one that uses an asphalt, a geosynthetic reinforcement. In this case, it was a polymeric geogrid, but instead of 125, 12.7 centimeters, it's going to be on the order of 7.5 centimeters, the asphalt overlay. And the concept was that this was going to provide equivalent benefit in terms of reflective cracking and equivalent benefit in terms of structural capacity. Okay, but this was deemed by the designers. But what about the similarities or differences in terms of carbon footprint, in terms of sustainability. So because we do have in this particular case 2 alternative designs that were deemed equivalent by the designers, and then we can go and calculate the carbon footprint of the conventional design and the carbon footprint of the reinforced design. I'm not going to walk you through the details on how this carbon audit was conducted, but as a reminder, we're going to quantify the carbon intake that takes the different stages for the materials used in each one of the 2 alternatives, for the energy or the construction, what it takes in the construction, and finally the transportation to take the materials from the origin, the initial source, to the site. We're going to do the carbon audit at the as constructed stage. The significantly additional benefits from the carbon footprint would come if we take into consideration the life cycle costs. And here are the results. So in blue, we have the conventional. Here in the top bar is the conventional asphalt overlay. In the lower bar is the geogrid reinforced case. In here in the horizontal axis, we have the embodied carbon in tons per embodied carbon per lane per kilometer. Remember, this project was on the order of 20 kilometers, 4 lanes. This is the benefit that we get in 1 lane, 1 kilometer. Compared here again for you to remind you what are the 2 different cross sections, and this is the difference in carbon footprint between conventional option and geogrid option. In blue are the material contributions to the carbon footprint, in orange the transportation contribution, and in green the construction. A different way of looking at these results is here. Organized black means materials, in this case asphalt, all the components, the actual material, its transportation, and its construction for the conventional design. The entire project, the asphalt overlay component of the project, is just one material, and this is the carbon footprint corresponding to the black, to the asphalt as a material, blue, the geosynthetic as a material, and the difference in relation to 100%, in this case 32%, 32.5%, is the savings in carbon as a percentage of the conventional design. This savings corresponds to 22 tons of carbon per lane per kilometer. As a reference, what is 1 ton of carbon footprint? As a reference, 1 ton of carbon footprint is the carbon dioxide that is sequestered by half an hectare of forest. So essentially here we're saving 11 hectares of forest in the carbon that will be sequestered by a forest of 11 hectares in per lane per kilometer of this particular site. A significant volume of savings in carbon footprint. And this is only one of the examples. We have done a significant number of additional examples, and systematically the solutions involving geosynthetics are more sustainable as quantified by the carbon footprint. And just keep in mind that when it comes to carbon audits, the use of asphalt, the use of cement have a significant content. It contributes enormously to the carbon footprint. So any reduction in thickness of asphalt, any reduction of any reduction on the use of lime, any reduction on the use of cement will significantly impact in the beneficial direction the sustainability of a project. All right, so after this, let me take you to some final remarks. I would like to convey again that the benefits of using paving geosynthetics are clear. We already know that, but in this particular case, we were able to identify better the mechanisms leading to the traditional use of these products, which is to retard or eliminate reflective cracking. I walked you and I hopefully convinced you that there's many different ways in which the geosynthetic can achieve this benefit of retarding the reflective cracking. Namely, one is what we call tension development. The other is what we call stress relief mechanisms. Once we know the mechanisms, we are able to put our finger into the functions that we need for the geosynthetic, and eventually the properties. In addition to that, we also can have geosynthetics that have a water barrier benefit. when installed. And essentially, when it comes to properties, we have some, I would call them more traditional properties that we have specified for these particular products: tensile strength, and tensile stiffness, and asphalt retention. But also I walked you through the importance of some, I would say, new or alternative properties as characterized for the cross shear testing and for the interface shear characterization. And that was all regarding reflection of cracks, reflective cracks. But in addition to that, we talked about the additional benefit that comes from using asphalt paving geosynthetics. In many of them, not all, but many of them will, in addition, provide an increase in structural capacity. And I walked you through a highly monitored field program monitored with asphalt strain gauges, with geophones, with moisture sensors. And essentially, they all led, and I showed you one of the responses, but I have equivalent results in many of the sections and from many of the sensors. They all showed, provided an early quantification of the structural benefit of using paving geosynthetics, in this particular case, when providing stress redistribution. And finally, I also walked you through the sustainability benefits that adopting geosynthetic reinforcements when using geosynthetics can lead, we can get when compared to more conventional alternatives, design alternatives, and in the particular example, and we studied this by examples, in the particular examples from Central Texas that I showed you, the benefit is on the order of 22 tons of carbon intake per lane per kilometer. And with that, I thank you so much for your attention, and
I'd now like to welcome our second speaker, Zara Kaya, Director, Civil Husker, Australia. Over the past 11 years, Zara has worked on numerous road and airfield projects in Australia in effectively addressing reflective cracking and helping deliver longer-lasting, sustainable pavement assets through reinforced asphalt using highly engineered geogrid technologies. In her current role as Director, Zara is leading Husker Australia's civil division, servicing the region of Oceania, which provides advanced engineering solutions across all disciplines of civil engineering, design, and construction. Please join me in welcoming Zara Kaya.
Hello, it's a pleasure to be here today, where we will be discussing optimizing pavement lifecycle using engineered asphalt reinforcement geogrids, looking at case studies with a focus on carbon emissions and material selection. Pavement deterioration is commonly experienced as a result of reflective cracking, and overlaying or removing and replacing the cracked asphalt is not sustainable, and in most cases not the solution. So what is a sustainable solution? Research and field verification over the past 55 years have demonstrated that by using engineered geogrids, we are able to absorb and distribute the stresses at the crack tip, and as a result, significantly delay reflective cracking by up to 4 times. This automatically reduces carbon emissions, maintenance costs, and disruptions to the public, while increasing operational productivity and asset life cycle. And here is a good real life juxtaposition as we move on to the case studies. This particular one is from Perth Airport, runway 06 threshold overlay with height at sea in 2009. We can see the condition of the existing pavement with extensive severe fatigue cracking in the existing asphalt, and underlying cracks had, underlying joints had reflected through. The airport wanted to do an asphalt overlay to maintain the pavement and to delay reflective cracking. High-tilted sea reinforcement geogrid was applied under a 40mm thick asphalt wearing course on top of a 25mm thick asphalt corrector course. We are looking at the condition 15 years after, free from reflective cracking, as confirmed and verified by the airport, despite the underlying cracks being quite extensive and severe. And here we can see the very latest condition, still free from reflector cracking and lasted long enough to receive surface rejuvenation to stop the loss of fines on the very top surface. Now, based on the designer's advice, consistent with field evidence, unreinforced asphalt would have lasted 1 to 4 years without reflector cracking, and that would have required 2 more surfacing to get to 16 years crack-free. So comparing that to the Heartily treatments applied, they achieved over 60% reduction in carbon emissions. Now, additional benefits include large cost savings in maintenance by eliminating additional surfacing costs, in addition to increased operational productivity as well as reduced fault risk for aircraft safety. Next one is an unbound runway pavement with an extensively cracked asphalt surfacing at Alice Springs Airport. We can see how wide the cracks were, and up to 150 millimeter deep. Design solution for 2019 surfacing was removing the top 60 millimeter of the cracked asphalt, placing the Heartily geogrid on the cracked asphalt surface, and putting back 60 millimeter new asphalt wearing course. All activities ran concurrently, returning the runway to service end of each shift. We can see on the left the profiling, followed by cleaning, spraying of bitumen, Heartily installation, and immediately after followed by the paving crew paving the asphalt on the right-hand side, as we can see. Here we can see the latest official inspection 5 years after, free from reflector cracking, despite the severity of the underlying cracks and the increased traffic during 2020 in this case. Now, designers advised the alternative design option was 100 millimeter thick asphalt with up to 10-year design life. Comparing that to the Heartily treatment chosen with up to 15 years design life, at construction, they saved 36% in carbon emissions, and per annum, this is about 57% reduction in carbon emissions. Again, the additional benefits go hand in hand with the savings in maintenance costs, as well as a reduction of fault risk and increased operational productivity. This particular one is a real-life project analysis undertaken by Brisbane City Council on an arterial road with severe cracking from the underlying cementitious base. 200 millimeter thick asphalt has been reported to show consistent reflective cracking in 3 years. In contrast, we can see here the performance of the section that was reinforced with the Heartily using 100 millimeter thick asphalt in this case, about 8 years after the surfacing. Council has reported gain performance of 100% increase in crack mitigation in this particular case, and gain performance of approximately 45% increase in service life because of the increased performance against reflector cracking, despite having used less asphalt in the treatment compared to the thicker asphalt treatment that they'd undertaken. Also looking at the emissions comparisons between the two treatments here, based on the data provided by the council and again IS materials calculator, the council was able to achieve 46% reduction in carbon emissions at construction, and this is about 62% reduction per annum, again because of the increased performance against cracking. The Brisbane City Council also was able to provide a cost comparison demonstrating cost savings achieved in this particular case, which was about 54% at construction based on their local rates and about 62% per annum. The additional benefits in this case being for a local council, cutting less meant reduced risk of hitting buried utilities, which was flagged as one of the other important benefits achieved for the council, on top of reducing disruptions to public and reducing the number of roadwork shifts required. This particular one is a direct comparison as verified by Transport for New South Wales, where the only difference is the inclusion of the high tilted sea within the asphalt on the left-hand side section. Everything else being identical, same age, same construction, same traffic, and we can already see a clear difference in the performance of the asphalt in terms of reflective cracking, in this particular case over a cement treated base as early as 3 years. This is another direct comparison, also verified by Transport for New South Wales. This time, the underlying pavement is a foam bitumen stabilised base. Again, same age, same construction, same traffic, and we can already see the difference in 3 years in terms of the performance of the asphalt, where the only difference is the inclusion of the high-tilted reinforcement geogrid within the asphalt. This particular one is a rapid exit taxiway at Sydney Airport, and what we are looking at is on the left, the condition of the prior asphalt surfacing in 5 years, which is quite extensively cracked, as we can see, compared to the condition of the subsequent asphalt surfacing in 6 years, this time with the high-tilted sea reinforcement. To resist reflective cracking from fatigue cracks, shrinkage cracks, as well as differential cracks, high-tilted reinforcement technology has been used in maintenance as well as in new construction. In maintenance, the typical application is a mill and fill with a minimum 40mm thick asphalt cover on top of the high-tilted sea, or keeping the existing and overlaying the existing with minimum 40mm thick asphalt if we can increase the height of the pavement. Here is an example reconstruction where high-tilted was incorporated, and this particular one is an example of a new construction where high-tilted was used within the asphalt over the brand new cement treated base in order to delay and mitigate the risk of reflective cracking in the asphalt. So what is high-tilted? It is a polymeric geogrid with an ultralight temporary geotextile backing and a bituminous pre-coating. Now you may ask, why even use an ultralight temporary geotextile backing? Now, that is required. It's a necessity for us to achieve ease of installation and quality of installation. However, that backing is designed to be penetrated by the overlaying asphalt aggregate for mechanical interlocking between the adjacent asphalt layers during compaction through the high-tilted geogrid. We will look into this a little bit more shortly and why it is important. Now, bituminous pre-coating is important because we want the asphalt overlaying asphalt to bond onto the geogrid strands as well. So to illustrate a little bit of what I was talking about, if we look here, I will just play the video. Hopefully it will work. So we can see here the underlying is a bitumen tack coat applied on the milled asphalt surface, high-tilted geogrid installed onto the tack coat, and asphalt paving taking place directly on top of the high-tilted geogrid as it should. Now, when the paving is occurring, we don't want the tires to pick up the underlying bitumen tack and start pulling the grid or the bitumen tack. So that geotextile, ultralight geotextile backing covers the bitumen and allows us a good quality installation. But once we start the compaction of the asphalt, as we can see here, once the asphalt starts being compacted, that ultralight temporary geotextile backing allows the aggregate from the overlaying asphalt to penetrate through and achieve that required mechanical interlocking as well as optimum adhesion between all 3 layers, underlying asphalt, high-tilted sea geogrid, and the overlaying asphalt. So how to select suitable geogrids for asphalt reinforcement? There are some important requirements. First, good bonding and interlocking for not just high shear resistance in asphalt, but also load transfer to the geogrid. Second one being resistance against construction damage during paving. Third, compatibility of the geogrid with the asphalt. And last but not least, end of life milling and recycling. First up, shear resistance. This particular field research undertaken by University of Texas on behalf of Department of Transport in Texas, it demonstrated that the geotextile backing type it has a direct impact on the interface shear bonding in the asphalt system. So couple of things to note about this particular research. It was fully funded by the Department of Transport, Texas, and therefore it is an actual independent study without a supplier involvement. The asphalt cores were obtained from in-service highway sections at State Highway 21. Each product was installed in line with manufacturers' recommendations in terms of the application and bitumen tack coat amount, and a control section with no geosynthetic asphalt and asphalt only was also included for a direct comparison and assessment of the impact using Leutner direct shear testing. Now, 6 products were tested. On the top, what we're looking at are 3 polymeric geogrids. The difference being GR1 on the far left was a polymeric geogrid with light permanent geotextile backing, which was 80 gram per square meter approximately in the geotextile. GR2 was a polymeric geogrid with ultralight temporary geotextile, which also had about 20 gram per square meter in the geotextile backing, and GR3 was also a polymeric grid with ultralight temporary geotextile backing, again 20 gram per square meter. The bottom 3 were glass fiber grids, the difference being on the left, a GR4 was a glass fiber grid with ultralight temporary geotextile backing, about 20 gram per square meter in the backing. GR5 was a glass fiber geogrid with heavy geotextile backing, about 150 gram per square meter, and GR6 was a glass fiber geogrid with no geotextile backing. The findings of this research show that GR1, which is the green one here, reduced the shear bonding strength significantly by almost half. Looking at GR1, it was a polymeric geogrid with light permanent geotextile backing. GR2 and GR3 were found to achieve the highest interface shear bonding strength and the closest to the control sample. As we can see here, GR2 and GR3 were polymeric geogrids with ultralight geotextile backing. Looking at GR4, which was a glass fiber grid with temporary geotextile backing, it reduced the interface shear strength compared to its polymeric version, as we can see. However, GR4 exceeded the shear bonding strength achieved by glass fiber grid with heavy geotextile backing, which is GR5 here, as we can see in the dark blue, which fell below the minimum pass-fail criteria set by in this particular research. Looking at GR6, which is a glass fiber geogrid with no geotextile backing, which also fell below the pass-fail criteria set in this particular research. The conclusions, looking at the conclusions of the research, the high bond strength witnessed in GR2 and GR3 polymeric geogrid specimens were attributed to the aperture size being 40 millimeter by 40 millimeter, the ultralight nonwoven backing to allow interlocking, and also the geogrids being pre-coated with bitumen. While the other polymeric product, GR1, which had a light permanent geotextile geotextile backing was found not to promote interlocking and therefore reduce the shear bond strength. You may have noted in the previous presentation that geotextiles perform more of a separation function, whereas the reinforcement function comes from the geogrid. So it is important to consider what is actually needed for the desired engineering outcomes when it comes to asphalt reinforcement. Another reason why good bond strength is important is for load transfer onto the geogrid. Research shows that the bonding of the geogrid to the surrounding asphalt plays a critical role in its reinforcement performance. And just how we achieve that good bond strength. Now, anyone who is in the asphalt construction industry will be very familiar with these three requirements that need to be achieved in any asphalt pavement: interlocking, adhesion, and friction. Now, when we incorporate a reinforcing geogrid in the asphalt, these requirements still need to be met, and it is important that they are met when we reinforce the asphalt. And just how do we do that? We are looking here at an asphalt core taken from a construction site where height of the geogrid is sitting 40 millimeter below the asphalt wearing, under a 40 millimeter thick asphalt wearing course on top of an existing asphalt. We can see on the left is the height of the C geogrid strand, and 40 millimeter apart from that is the adjacent height of the C geogrid strand that we can see on the asphalt core. And right through them, what we're seeing is that stone and stone connection between the adjacent asphalt, which is very important in optimizing both interlocking and friction, but also achieving optimum adhesion between the three materials: underlying asphalt, height of the geogrid, and overlaying asphalt. Because please remember that underlying bitumen tack coat bonds not only height of it onto the underlying asphalt, but also the overlaying asphalt onto the underlying asphalt as well. And that is achieved through the ultralight temporary backing of the height of the geogrid, the 40 millimeter by 40 millimeter aperture size, allowing the over a 80% open area across the pavement. We reinforce with that opening, and also the bituminous pre-coating of the geogrid itself, which it makes it highly engineered for asphalt reinforcement. So when we use the right geogrid, we achieve almost identical shear bond strength to asphalt and asphalt only, as corroborated by various independent research. Next one is, why is resistance to construction damage critical? Survivability of the grid directly impacts its effectiveness, and different geogrids perform differently in surviving the paving and compaction damage, which is a mechanical damage that occurs directly on asphalt grids. Research shows that polyester and PVA, polyvinyl alcohol polymer geogrids have much higher resistance to construction damage compared to geogrids made from brittle raw materials such as glass fibers. Now, the raw material also has an impact on the long-term performance of the grid. Research also shows that polymeric grids have much higher resistance to dynamic loading compared to glass fiber grids, and from a longevity perspective, it has a great deal of impact. So if we look at here, the glass fiber grid strand broke between 16 to 21,000 cycles under dynamic loading when shear stresses were applied, whereas the polyester geogrid strand did not break at 160,000 cycles and the testing was stopped. Polyester and polyvinyl alcohol polymers are compatible with asphalt for a number of reasons. One I will mention is their thermal expansion characteristics being very similar, which means the grid and the asphalt behave similarly and they work well together, which is important in service, but also for future recycling consideration when we think about the use in RAP as well. The second thing I will mention is that if we are to apply the reinforcement geogrid directly on a concrete pavement surface, which we can, it is important that only PVA geogrids are used, which is polyvinyl alcohol geogrids, because they have high resistance to alkalinity. Otherwise, the alkali attack from a concrete surface will have quite a negative impact on majority of the other type of materials that do not have high resistance to alkalinity. So it is important to note what would be suitable and what would have the right type of compatibility chemically and mechanically. Well-engineered geogrids can be milled and recycled, and at the back of 50 years of experience with high tillet technology, what we recommend is cutting 5 to 10 millimeter below the high tillet or staying above the high tillet if we want to keep the geogrid in. Here is an example of milling from Hume Highway, where they cut 5 millimeter below the high tillet level, which was 55 millimeter below the finished surface level. And we can see the milling operation without any disruptions under live traffic. And we can see the stockpile with wrap containing high tillet C fibers brought to the plant. And here we can see the screening results, material passing 20 millimeter, consisting of mainly wrap with only small fibers of high tillet C, which can be fed into 20 millimeter wrap for asphalt production. And here we can see the final finished product. This work was done in collaboration with a major asphalt producer, through which it was confirmed that reclaimed asphalt containing high tillet was processed quickly and efficiently, and there were no blockages observed. And this positive result was observed despite having cut only 5 millimeter below high tillet, which is operationally a positive outcome. For any further information or guidance, please do feel free to contact us, because we are absolutely able to maximize the sustainability benefits achieved with this technology. Because this allows us a well-engineered, sustainable geogrid with demonstrated decarbonization outcomes throughout the life cycle. For anyone who may be using IS Materials Calculator, if you go into asphalt and bitumen products and type Husker, you will see various high tillet materials listed there as well. So bring it all together. Really, in summary, this is about getting more with less. And based on 55 years of field performance, both globally and in Australia, highly engineered asphalt reinforcement geogrid solutions have been independently verified to provide up to 4 times resistance to reflective cracking and increased service life in roads, ports, airport pavements, in both existing and in new pavements. High shear resistance for high shear applications, and up to 75% maintenance cost savings per annum, along with average of 62% reduction in carbon emissions per annum. So all of that is delivering low carbon, low cost, resilient pavements, importance of which we are reminded of daily. Now, getting more with less also applies to the geotextile backing of the geogrid. There are 3 geotextile backing types in the market that can be supplied by various manufacturers, including Husker, and different types of grids. So it is not a supply issue. However, it is important to select the right type of geogrid and the right type of backing in line with the desired engineering and sustainability outcomes. So comparing these 3 types of geotextile backings, we can see the ultralight type involves low carbon, and the lowest effort and energy when it comes to future recycling compared to light to heavy geotextile involving 4 to 7.5 times the energy and effort. Additionally, the ultralight geotextile backing type has been demonstrated to provide much higher shear resistance for asphalt performance, and it is more suitable when used with warm mix asphalt. And going to the heart of it, which is reinforcement, ultralight backing enables the reinforcement function, and we're able to achieve that reinforcement function. Whereas with light to heavy geotextile backings, separation function from the geotextile needs to be considered when we are assessing what would be the right type of geotextile backing, because it's important to consider these for us to engineer both high performance and sustainability. This is the end of my presentation, and I look forward to discussing the questions. Thank you.
Thank you, Sarah, for your insights. Well, now it's our audience's turn to get involved. So big thank you to everyone who submitted questions for today. So without further ado, why don't we jump into our first question? Now, the first one's come through from Araj, who's in South Australia, and I'll direct this one to you, Sarah. The question was, what testing methods are used to validate the performance of sustainable reinforcement materials?
Thank you very much for that question, Megan. There is extensive verification of performance by research, and one I can very quickly show is a dynamic testing undertaken as part of a doctoral thesis where pre-cracked asphalt was overlaid with a new asphalt where the underlying pre-crack was 3 to 9 millimeters wide. And the research compared the performance of reinforced and unreinforced asphalt under the exact same conditions. So here we are about to see once the slide moves, we should be able to see the typical crack without the reinforcement. Now we're about to see the typical crack without the reinforcement, where note that as part of the research, the asphalt system was painted in white so that the researchers could demonstrate the cracking pattern, and we can see the pre-crack opening on top of the base asphalt layer underneath the new asphalt placed on top of it. We're about to see the typical crack without the reinforcement. The moment that the crack reaches the surface is the end of exerted fatigue testing, and the recorded number is approximately 80,000 cycles. So by the time 80,000 dynamic fatigue cycles were applied, reflective cracking reached the surface, and that is considered the point of failure. Now we're about to see the typical crack where the only difference being the inclusion of the high-tilted C geogrid directly on the pre-crack opening before the asphalt overlay. The moment the first crack reaches the surface is the end of exerted fatigue testing, and the recorded number is over 500,000 cycles. So the research has concluded that as part of this particular study, the improvement factor to be between 4.6 and 6.1 times. Now, this is consistent with numerous other scientific research, and also the field experience. And I'll be happy to provide more information and more papers. I forgot the person who asked the question. I apologize, but if you could please reach out, very happy to share more details.
Thanks, Sarah. I think you'll definitely get some people reaching out after today's presentations. Now, I've got a question which I'll direct to the two of you. So, and it's come through from Adnan from New South Wales. And the question was how to incorporate such geogrids in pavement design. Jorge, maybe did you want to kick off or?
Yeah, I can give it a shot. So the core of much of the research that we're doing is the fact that these polymeric geosynthetics have been used for a long time to mitigate or to retard reflective cracking. But in addition to that, and this is a bonus, but an important bonus, some of these geosynthetics can also provide an increased structural capacity. So there are two aspects in the design: the design to provide increased structural capacity and the design to retard the reflective cracking. When it comes to design to provide additional structural capacity, I showed you some of the results from experimental tests and from field tests that show that for a given load, we will have substantially different elastic strains when we do have a reinforced asphaltic layer and when we do not have such a reinforcement. From those differences in strains can be translated into a modulus, and that modulus can be translated, for example, in a difference in thickness in the asphaltic layer that you would need when using and when not using asphalt reinforcement. For example, SH21, which is one of the examples that I showed, the main problem was increased traffic, mainly because these are roads that are subject in the energy sector. So we need to increase the structural capacity, but we do not want to reconstruct the road. And the strategy that was used was adopting asphalt reinforcement because we wanted to, the Department of Transportation wanted to increase the structural capacity and at the same time mitigate a problem associated with reflective cracking. I'm going to let Sarah answer the question regarding the design for retarding reflective cracking.
Thank you very much for that, Professor Thunberg. Look, in Australia, especially the predominant use of geogrids like high tilted sea have been for mitigation of reflective cracking. And the design approach is simply adding the high tilted sea geogrid, or whichever one will be high tilted XB, depending on what surface we're working on, adding that to the asphalt, whether in resheet or resurfacing or an overlay application, or it could be a patch repair, reconstruction, as well as new construction. And I can see some of the questions have been asking about new construction use. So particularly if the underlying is a cementitious base, or it could be CB, it could be lean mix or concrete pavements, quite commonly incorporated in the design by adding it within the asphalt, into the asphalt, whether it's new construction or maintenance of existing pavements. Now, for anyone interested, there are design methods available which helps demonstrate and calculate the life of the asphalt against reflective cracking with and without the reinforcement. Again, anyone interested, please feel free to reach out. We can provide more information. But really, it's very much an evidence-based practical approach in design here in Australia, that it's incorporating it where reflective cracking is expected by adding it to the design in both maintenance as well as new construction. Now, I know that there are a number of designers who are interested to see the development of the design method when it comes to the structural design with such geogrids. So I'm sure there'll be lots of interest in your further work, Professor Zomberg, in that department.
Thanks, Sarah. Another question is maybe if you could specify the correct geogrid material and installation procedures.
Yes, look, something that's quite important in that is really, especially for anyone who may be new to the asphalt reinforcement technology, I would encourage for them to please reach out for advice, because it will be important to understand exactly what type of pavement we're working with, what type of surface we're working on, and we will be able to assist with the appropriate specifications around the installation as well as just the material specifications. It's not complicated. However, it is just understanding what type of material, where, what are the installation specifications around that, because that process ensures quality installation, and that quality installation ensures the right outcome. So I would simply recommend that please reach out and we'll provide the right information.
Awesome. Thank you. Jorge, I've got a couple of questions which have come through live that I might hand over to you. They've come through from Narisha. So big hello to Narisha for watching live today. So there are two questions. The first one was, what is the order of the design traffic loading in the test section of SH21? If you want to do that one. And then there's also, there is a significant difference. Did the research make its way into the design guidelines to assess reduction in the thickness of structural layers or increased remaining life? I hope I've positioned that well, but if I can hand those questions over to you.
Yeah, so thank you for the good questions. And I think that there are so many good questions that came live. So, well, the SH21, which is this particular project, is a high volume road. I will need to get back to you with the actual traffic, but it's considered a high volume road. It is part of what is the energy sector in Texas, which means that we expect to see a significant increase in the traffic volume over the design life of the structure, and this was the case in here suddenly. So that's why was the significant need, the important need of increasing the structural capacity. In this particular case, and I showed some cross sections, the original design was considering an overlay of, I'm thinking in inches, so it's 5 inches, which is 12.5 centimeters, and the without asphalt reinforcement, and ended up being 3 inches, so 2/3, 3/5 of the original design when using the asphalt reinforcement. The basis for this selection, so essentially we're talking about 5 centimeters out of 12 centimeters that were the decrease in the thickness of the asphalt overlay. The basis for these were preliminary data on the differences on the reduction in strains when using equivalent systems with and without asphalt reinforcement, and this was validated actually with a much heavily instrumented data that were collected, heavily instrumented sections that are leading to data that validates the selection that was done by the designers being the Texas Department of Transportation. So not only they went for this particular design, so essentially for a given design life, they are reducing the thickness of the asphaltic layer. And that was a significant reduction that is being confirmed with the instrumentation data that we get in terms of strains for a given loading.
Well, hey, while I have you, there was a question. Well, I saw a couple of the live questions came through with regards to cross shears. So one was from Reza, and it was, have you considered the effect of fatigue on the results of cross shears tests with geosynthetics?
Yes, and I went very, very quickly on that. So in the cross shear testing, I showed two types of results. The type, I could say more of an index type of test was a monotonic test, a cross shear test that provides the increase in the peak interface, a peak cross shear test, cross shear strength, and also the increase in what we can call the ductility of the system when having the polymeric geosynthetic versus when the control section without it. Now, I'm going to come back to the fatigue. So I feel that this is particularly relevant because what this says is that one thing, is we have a higher peak cross shear strength, and we want that. Higher peak means that the reflective cracking is going to be retarded. But the other important thing is the presence, and if you remember, there is a curve, interface shear peak, and then it doesn't drop to zero, which is what would happen in a brittle system. It remains. There is an interface shear that remains. That is very, very important because, in my opinion, and based on the evidence that we have, what it does is that once the crack develops, the crack, when you have the reinforcement, it doesn't stop resisting. And this will reflect into, rather than having a crack and suddenly having a humongously long crack, even if you reach the peak and the crack originates, this is not necessarily going to propagate as quickly as it would without the asphalt reinforcements. So it's not only the initiation of the crack, but also the extent to which that crack will occur. That goes from the monotonic, but maybe your question is on the fact that this is actually cyclic loading, and I didn't have the time to present much about it, but we also run cyclic cross shear tests, and the way that these results are reflected, which is essentially an evidence of the fatigue, and essentially they show that with increasing number of cycles, there is a decrease in the shear resistance across a given surface, and the plateau where that remaining resistance after a significant number of cycles occurs is significantly higher when we have a polymeric reinforcement than when we have the control section without reinforcement. So in a sense, we are measuring the fatigue or the impact on fatigue by evaluating what is the cyclic residual dynamic strength that we end up having with this cross shear testing. So I'm very, very optimistic about the results that we get with this cross shear testing, both from monotonic tests that I recognize that are a good index, and from the cyclic tests that potentially are the basis for design. Thank you for the good question.
Thank you. Now, Sarah, I've got a question, really quick one, because I think I'll then be throwing to final comments from you both, but it came through from Ray. Is it necessary to fix the existing crack first before setting up the geosynthetic? And I'm hoping that's a short answer.
It's a very short answer. Look, all we need to do if we have a crack surface, if the cracks are wider than 3 millimeters, we recommend filling them with a bituminous crack sealant because it's best practice. And then we can proceed with spraying the bitumen tag, installing the geogrid, and then placing the minimum 40 millimeters of asphalt overlay, provided what's applied is a high-to-lid type technology. Now, it is important that pavement needs to be structurally stable. So if the pavement is structurally stable, you don't need to do anything for the cracks other than filling the cracks, basically.
Thanks, Sarah.
I hope that's a short enough and thorough enough answer.
Thank you. Look, what I might do, I think we've run out of time, but my final thing I would like to pose to you both is if you'd like to offer any final comments to our audience. I can say we've had a massive audience today, so if you would like to, your final thoughts or key takeaways from today's presentation. So, Jorge, if I start with yourself, and then I'll hand over to Sarah to end today.
Yeah, my final thoughts, and is more of a message to those of you that are pavement engineers that are not used to design roadways using geosynthetics. And my comment comes from using geosynthetics in roadway applications way beyond asphalt reinforcement, which is the focus of this presentation, of this great discussion. So my message is geosynthetics are engineered products, and as such, we need to, even though we have a significant volume of past evidence and past experiences, I want to emphasize the importance that we're going in a direction in which we are understanding more and more. Whenever we use geosynthetics in roadway applications, we need to ask, what are the mechanisms that are making this application work? And if we know the mechanisms, then what are the functions of the geosynthetics that make it work? And if once we know the functions, what are the properties that makes these geosynthetics work? So my message is there are many tools that as a roadway designer you have at your disposal, and my encouragement to you is to consider the use of geosynthetics in your portfolio, because these are highly engineered products, and we know a lot, not only that they work when used appropriately, but also we can get to the bottom of why they work the way that they do and what are the properties that make them work. Thank you.
Thank you. And Sarah?
Thank you, Megan, and thank you everyone dialing in today. Look, my only message is we engineer the decarbonisation outcomes, and as part of that, engineering both high performance and sustainability in the materials, in the right materials we choose for the application will be quite important. So I hope that the message is clear that we can deliver higher performance resilient pavements, and I hope that we do that in the most sustainable way that we can. Thank you.
Thank you. Thank you both. So look, I think that's all the time that we have for today. So please join me in thanking our speakers, Professor Jorge Zornberg, who's joined us live from Austin, Texas. So big thank you to Jorge and to Sarah Zakaya for their time and input. I'd also like to thank Engineers Australia's industry partner, Husker Australia, for their support today. Now, to help us to improve and plan our future sessions, could I please ask that if you could complete the short feedback form, which is linked in the description box below. Any insights that you provide is most welcome. And finally, thank you for joining us today, and we hope to see you at our next Thought Leaders event. Good afternoon.